So, am I recording? Oops. I am. Okay, cool. So the problem was from chapter 7 lecture packet. And it was number 14 C, which is asking for the abbreviated electron configuration for chromium. Right, so we're looking for the abbreviated electron configuration for chromium. So, first thing we gotta do is go to our periodic table. We see chromium is in the 4th row here, right? And it's 1, 2, 3, 4, 5, 6 valence electrons, right? Everybody cool with me still? And if we look to the previous row, we see that the noble gas from the previous row is argon. So our electron configuration will start off with, oops, sorry, little r.
On the answer key, you had it as with the 3+ charge. So that's how I did it.
Oh.
Yeah, so that, yeah.
Oh. Cool. Well, let's just do this first.
Okay.
So we've got argon, and we know it's in row 4, so the s orbital that we're starting with for our valence electrons is the 4s, right? And how many electrons can be in the s orbital? 2. And then we go one lower for the d orbital in that row. So we have the 3d, we had 6 totals, so that gives us 4, right? Questions about how we got here?
No.
Okay. So there is a tendency that transition metals have tendency? I don't know, whatever, you guys get the point. To fill the d orbital halfway or all the way. Okay? So, it's very common to form a D5 and a D10. And the reason being is because it's a bit more stable energetically. Sorry. Right? So, if we can form a D5 or a D10 with an element, we usually will, okay? Even if we have to take an electron from what is technically a lower energy orbital, the 4s and the 3d are very, very close in energy. So it doesn't take a lot of energy to take one of these electrons and put it in the d orbital, but it does give you back this bump in stability, right? So even though you have to add energy to get one of the electrons to go from the 4s to the 3d, you gain a net of lowering the energy of the overall atom. So what we actually have for chromium is argon 4s1, 3d5. Okay. Now, this is an exception, right? Not everybody does this. And you'll now be tested on that. Exceptions. Oh my gosh. Okay. In past semesters, especially when we're in class, we can go over this topic in much more detail. And so I go into that and I explain it. If you look in your textbook, it will have the electron configurations given for all of the transition metals. And what you'll see is that some of the elements do this and some of them don't. The farther down you get in terms of rows, the closer together the S, D, and P orbitals in that row will be in energy. And so you get some weird electron behaviors happening because of that.
So it only does that if it's going to D5 or D10?
Correct.
Okay, so it wouldn't be like if it's like a 3D, like, and it gets like to a 6.
Exactly. There's no added stability in the 6, right? It's just a half full gives you an orbital diagram for your d orbital that would look like this, right?
Okay.
And that half full d orbital gives you a little bit of extra stability, right?
Yeah.
But again, those are exceptional cases, and that's not going to be something you'll be tested on. So for what I want you guys to know for electron configs and orbital diagrams is just the basics, okay?
Is that something that we'll need to know for 201?
Not really. I'm trying to think of when you might need to know that stuff. For you, Harrison, I think you're going on to more chemistry. If you go to inorganic chemistry, you may see electron configurations again, but it's not a big part of general chemistry or organic chemistry, especially not when you get into transition metals, right? So transition metals in particular you take an entire class on transition metal chemistry because they're weirdos. So yeah.
Okay.
Sorry, go ahead.
I just have one more question.
Yeah, go ahead, Maya.
But on the answer key for 14F, you took out the 4F14, and I was wondering if that was a mistake or there was a reason.
No, so usually what I would tell students is because we never deal with the F block, I don't care if you write it or if you don't, basically.
Oh, okay.
Yeah, so basically if you were to write it, it's technically more correct, but I don't require students to know what's going on with the F orbital. So I would mark it correct if you gave me the F orbital, or if you didn't. Don't care.
Okay, thank you.
Yeah. Did somebody else have a question?
Yeah, I was just gonna. So after seeing that one of the tendencies is also 3d5.
Yeah.
Is that why iron's configuration can be 4s1 3d5?
4s1 3d5. Yes. Mm-hmm.
Okay, got it.
And you're talking about the iron ion, I'm presuming.
Sorry, iron 2+.
Yes, exactly. Right?
Got it. Because I think it was one of the problems on the practice.
Yeah. And that's one of the things that that gives you a little bit of insight into why certain ions are more favorable in the transition metals than others, right? So when you look at the electron configurations, you're thinking about what's adding stability to this, right? So which electrons can I lose with a low cost, or maybe even when I lose a couple of these electrons, now I've added a little bit of extra stability to the ion, right?
Uh-huh.
So that's kind of what we didn't really get to cover much about this, but that's the point of learning about the transition metals and their electron configurations.
Okay, awesome.
Yeah. And it's a very complicated question, to be perfectly honest. So, you know, that, like I said, there are some elements, some transition metals that do this and others that don't. So it really comes down to calculating the energies of these electron transitions, which is a very complex process, not something that we need to do. And so there are a lot of exceptions to this, which is why, again, you won't be tested on that.
Got it. Thank you.
Yeah, absolutely. Any other questions about these? All right.
Just to like confirm, so is that why on H, on 14 H and I, the d orbitals are filled all the way instead of like
Yes, exactly. Mm-hmm.
got it.
Yes, exactly.